All right, so good morning. I'm Alexandre Gramfort. I work at INRIA in the parietal team. I'll show a few results and also methods that we've been working on to work with different data sets and what it means in terms of statistics. So let's just to frame what we are trying to do, and we have some brain data, let's call it X, and we want to predict some outcome. Let's say if we want to predict if the subject has a disease or not, so control versus patient, or if we want to predict, for example, if the subject saw a house or a face in the scanner. So it's typical decoding. In terms of statistics, what we're trying to do is learn a function f that will take x as input and will output y. So going back to this example of face or house, this is a graph that shows you here on the x-axis you have the number of sessions that you have for training, and when you have on the y-axis is the accuracy of the classifier. So this is all data. This is the data from the Haxby paper from 2001. And what you can see is that the more data you have, the more the accuracy is big. So these types of analysis are people call learning curve, and it shows you that the more data you have, the better. Wow. So you also see something interesting in this figure, which is that provided that you have enough data, you almost have perfect accuracy. So if here I've got 6 or 7 sessions, you almost have a rock IUC of 1. So you say, amazing, the more data I have, the better it works, and if I've got enough data, I've got perfect prediction. Now the story in practice is usually a bit different than this. So to see this, let's see what the problem can be. So let's say we want to increase the sample size. So we want to augment the number of points that we have access to for training, but usually when we try to do this, you may end up pooling data sets which are coming from different devices, different scanners. If you pool EEG data sets, maybe you have different channels, fMRI sequences, or maybe you pool data sets that have been pre-processed in a different way. You have different populations for ages, different sex, clinical disorders. And sometimes you also have the clinicians, the medical doctors that have annotated the data that have just been given different instructions to put the labels. So in practice, by pooling all these data sets to have big data, you end up in a scenario where actually the performance can go down. And also the performance, when you evaluate it on new left out data, can also drop. So to convince you, I took this example from a different world, from computer vision, and what you see here on the panel, so it's a system that tries to predict from an image if you see a car, if there's a car or not in the picture. You have 5 different data sets, sources of data, and what you see on the left is that if you train on ImageNet and you predict on ImageNet, you have this light blue curve, and you see that you predict a bit better when you predict a bit better on ImageNet if you train on ImageNet. So, but the difference is not completely huge. But if you look now on the right side, you see that if you train on Caltech 101 and you test on Caltech 101, you're super good. But now if you test on other data sets, the performance is really bad. So people sometimes mention the problem of dataset bias, but this is a very general problem. How do you generate insight from new data sets that may have different distributions? So in order to understand this, we'll give you different insights of what can happen. So I will basically say that you have a shift in distribution. So let's say you want to do binary classification and you have a 1D brain, so you're in one dimension, you have a single voxel, and you have class 1 and class 2, and this is your training data. What you would do, naturally, is to find a decision function that splits the blue part from the green part. And now let's say you want to test on new data, and if the same test data have the same distribution, then you're very happy because this decision function also is perfect for the test data. Now let's see what other scenarios that can happen. So you can have a distribution shift like this, where basically just the classes go more further from each other, and you have a distribution shift, but you may not have error. So you have this shift, but still no error, so you can have still an optimal decision. Now, the other scenario. Let's say you have new data, and you have a shift in distribution. So it's just your samples that are just moved to a different part of the space just because it's coming from a different source of data, as the source of data. And now if you're trying to find your optimal decision from data set 1 and you try to generalize to new data, you realize that you make errors. So your decision function from the training set is not optimal for the test set. So how do you fix this? So the first way to fix this is what people call domain adaptation. And it's an unsupervised way of addressing this very common and classical problem. So the overall goal is to make sure the distribution of the test data matches the distribution of the trained data. So what you see with this tiny picture here is that you basically want to make sure that you can find a way to go from one source of data to the other one. So there are different ways to do this. You can find an optimal subspace that basically prevents you from saying that the distributions are coming from a different source. So find a representation in which you cannot anymore say if the data is coming from source 1 or source 2. You can also try to do matching of moments. This is what we call the Corral method, that is matching second-order moments. And there also recently has been a lot of efforts using optimal transport to move this distribution and to address this problem of shifts. In this scenario, you have unsupervised data. It means on your new data that you used for testing, you don't have any labels. Okay, so let's say you want to predict on another clinical site and you have no single label on this new clinical site. There's another scenario that you can consider, and another fix is to what people call transfer learning. You can also see this as supervised domain adaptation. What you're trying to do here is you have a source of data that you use for training, and you want to predict the new data, but you have a few label points on your test data set. And the idea is that you want to adapt the model that you train on source 1 in order to work on source 2 by feeding it a few labeled data points. The cartoon picture that you see on the bottom left is basically showing you that if you start from a pre-trained system, then you are already better than chance, and the more data you have, the bigger it goes. This is the dashed line. Whereas if you only start from scratch with the few data points that you have on the what I call the target domain or the objective source of data, you start from 0 and it goes slower, and eventually you may not even raise the same asymptote. So, but for this, you need to have a few labeled data points on your target domain or test data set. So now let's look at what this means in a practical problem. So I'll use this problem that people call sleep scoring. So it's the context of sleep disorders. It's a classical clinical exam where you put people with these types of electrodes and you get a night of data. And you have one label per 30 seconds of EEG recordings, and the game is to predict in what sleep stage people are. So people call it polysomnography or PSG. You have multiple sources of data, and the game is the following. You have some input time series for 30 seconds, and you want to predict a class which is either awake, rapid eye movements, or stage 1, stage 2, or stage 3, which are the different stages of sleep. So it's you can see this as a multi-class classification problem. All right, so now let's see what happens if you try to do these types of scenario where you train. So here we train on a data set called MESA, and we test on the mass data sets, which is the mass has something like 60 records, so 60 nights, so 60 subjects. What you see, what you see in S means when you only train on source and you predict directly without any adaptation. And what you see is that if you use domain adaptation, you go up. Okay, so every dot is one subject. So you basically each of the subject, what is the accuracy you get for this particular subject. You can do this because you have an entire night, so you've got hundreds of samples per subject. And you see that different ways of doing this adaptation, and some work better than others. In this particular application, the methods based on optimal transport are outperforming the others. Now, let's look at the example of transfer learning. So we take the same data sets, and what we're trying to do now is we start from a pre-trained system, so it's actually a convolutional network here. We start from a pre-trained network that we trained on the MESA data set, and we try to predict on this mass data set. And what you see is what you had on the cartoon picture, that if you start from the pre-trained network, you start much higher, and you eventually reach also a higher value. Okay, so what you see here is that the orange one is a bit higher than the black one. Okay, so by using this pre-training and doing some adaptation, you can do better. But again, for this to work, you need some labels on the target domain, which you may not have in all applications. So yes, so what you see here is that this is improvement compared to no pre-training, and here if you were to do some adaptation. So the dashed horizontal line is if you just do unsupervised domain adaptation. So of course you see that if you supervise a bit better, supervise it works better. All right, the second problem I wanted to mention is the problem of variable noise level. So let's say you pull data sets from different sources, and for whatever reason, your data sets come with different noise amplitudes. So if I would picture this, let's consider linear models. So we have k sources of data, so from, let's say, y1 to yk. And we assume that each yk can be linearly expressed from a set of features which are different across data sets, but you have the common regression coefficient beta. So you need, of course, to have the exact same number of variables for each of the conditions. So let's see, every voxel is, for example, one MRI voxel. That can be one EEG channels. That can be many things. Okay. And the big, the important thing here is that assume, besides this linearity of the model, I will assume that I've got some additive noise, and that the additive noise is different for every data set. Okay, so this is what you see here. You have sigma 1, which is different from sigma k. So if you want to be fancy, you will say that you have heteroscedastic noise models. Each of your observations are not corrupted by the same amount of noise. But the noise is the same for every domain or every source of data, and you know the source. You know where your data is coming from. So now I apologize for with this complex slide, but here, let's say you want to find beta. So a very classical way of doing things is using the lasso and sparse estimator, where you have a data fit term that you see here, and then you have some regularization. Let's call it an L1 norm, something that promotes sparsity. It's not super important, but something that will basically work when you have a lot more features than samples, when you a higher dimension than the number of observations you have. There's something that the theory tells you is that the regularization parameter should be proportional to sigma star and the square root of log p over n. So if you're wondering why people have been excited about component sensing, is because you have a log here. That is the magic thing. The problem here is that for this lambda to work, you need to know the noise level. And now imagine if your data is coming from different sources and you use these types of estimators, and every data point is corrupted by a different noise level, then obviously you have a problem. You cannot have a lambda which is different from every source of data, because the lambda is common and the lambda is in the beta, in front of the beta coefficients. Now you can look a bit what people have been doing in statistics, and for example in the world of robust models. You can change the estimator and now try to estimate not only beta but also the noise levels. Okay, so it's a tiny change where you basically now have also the sigma at the denominator plus some term that you can see this as the regularization on the noise model. And the beauty of this estimator is that then the lambda parameter doesn't need to depend from the noise level. What it means in practice is that if you have data which are a higher noise level, you should not change lambda, which can be a very interesting thing. So now imagine that you pull data from different sources. I will give you an example just after what it can be. You can just estimate all your noise level for different tasks or domains, and then find your estimator beta. So it's a joint estimation of the regression and the noise for every sources of data. So here an example in a world I know quite well, which is the world of EEG and MEG, and you basically have now different sources of data. You can see EEG or MEG graduators or magnetometers as three sources of data. And the game in regression that is here is to find where in the brain is the signal coming from. And just a long story short, if you use these types of models, you can actually improve the recovery of the active sources in the brain. So I will progressively stop showing you some code, and I think that's it. Thank you very much.